Hello everyone, welcome back. So today we'll take up some more problems from mechanics. So let's begin with the first question. So we have a thin and solid rod, okay, whose length is L and it is leaning against a smooth semi-cylinder whose radius is 1 meter, and the cylinder is actually fixed to the horizontal plane. Now the lower end of the rod A is held on the ground and then it is released from rest. Okay, so initially the situation is something like this. So the tangent, so the contact point is at an angle of 45 degrees from the horizontal, right? And the rod is now released from this current position. So the rod falls sliding against the side of the cylinder. So we have to neglect friction everywhere. And the questions are, what is the angular velocity when the upper end B reaches the cylinder, reaches the surface of the cylinder? Okay, so that's question number one. And the other questions we'll talk about them after a while. So they're basically related to the first part itself. Okay, so let's draw a diagram and discuss the concepts. Okay, so this is the diagram of the initial situation. Okay, so this contact point initially made an angle of 45 degrees, right? So and also this point is the center of mass of the rod. So the height of the center of mass in the initial situation is r by square root of 2, and in the final situation when the edge of the rod reaches the cylinder surface, so at this instant, let's say the angle made is some theta, so the height is going to be, and now by similarity of triangles we can figure out the height that the center of mass dropped by. Okay, so the larger triangle, so the height of the larger triangle is r sine theta, so the height of this half right triangle, so the height of the small right triangle will be r sine theta by 2, right? So this height is r sine theta by 2. So this is the final height of the center of mass. So the drop in height of the center of mass is r by root 2 minus r sine theta by 2. Okay, so the reason I'm writing down the drop in center of mass, drop in height, is because we want to use energy conservation, right? Because our ultimate goal, because what we want to find is the angular velocity, and for that we'll use the energy conservation method. So okay, so now I'm drawing a general case. Okay, so this is not the initial case. So this is, I'm assuming, a case after some time delta t. Okay, so here basically the rod must have gained some angular velocity, and so this bottommost point that is in contact with the floor, it clearly moves along the horizontal, right? So I'm just marking it with the rightward arrow. Okay, so now the thing is, if we can comment on the velocity direction of any other point on the rod, then we can locate the instantaneous axis of rotation, right? And that point is the point of contact between the semicircle and the rod. So this particular point, by constraint, we can see that it cannot have a velocity in the normal direction. The reason for that is the semicircle is actually fixed, right? The semi-cylinder is actually fixed, which means the rod, if I want to draw the velocity of this point, the rod cannot have a component of velocity in this direction. So the direction of velocity at this particular point will be along the tangent. Okay, so from here we can fix two direction of the velocity vectors. So if we draw perpendiculars to the velocity vectors, they will intersect at the instantaneous axis of rotation, right? So the thing is, we are not interested in this case. We are interested when this NB of the rod reaches the surface. Okay, and that case is not so different. Okay, so it looks something like this. So again, the bottommost point has a velocity towards the right, and the velocity of this point B, exactly similar to the explanation we had here, the velocity vector at this instant will be along the tangent or along the rod. They're both tangent to this point. If you want to draw a diagram after the situation, the diagram is going to be a bit different. Okay, basically after this point, what will happen is the rod will still slip on the cylinder for some time, but the difference is that now the velocity vector won't be along the rod. The velocity vector, in fact, okay, so the velocity vector will be along the tangent. Now the rod is not a tangent to the circle anymore. It's kind of like a secant, right? It will only be tangent till this instant. Okay, so after this point, the rod will be inclined at another angle to the tangent to the semicircle. So anyways, we are interested in this case when the rod just reaches when the end just touches the cylinder. Okay, so now we can easily locate the instantaneous axis. Okay, so just to make the diagram a bit more compact, let's make the rod a bit shorter, right? That way the lines won't be too long. So now let's draw a perpendicular to this velocity vector, and similarly a perpendicular from the other velocity vector as well. And the point where they intersect is the instantaneous axis. Now, once we know the instantaneous axis of rotation, we can determine the kinetic energy of the rigid body, right? So one way to write the kinetic energy of this rod is by using the general formula. So that was half total mass times VCM squared plus half I about the center of mass times omega squared. So this was the general formula, but if we know the instantaneous axis of rotation, then we can also write it as half I about the instantaneous axis times omega squared. Okay, so now this line over here, guys, so this was perpendicular to the velocity vector at B, right? And the velocity vector was along the tangent. So this line is actually the normal to this. So if I extend it, it should meet at the center of this circle, right? So this line is a perpendicular. Now the length of the rod was given to be 2r. This angle was theta in our discussion. So even this angle is going to be theta. So from this right triangle over here, we can see that tan theta is 2. Okay, so now observe this right triangle over here. So the length, so this length over here, like the perpendicular length, it will be 2r multiplied by tan theta, right? So this length is going to be 2r tan theta. Okay, and similarly this length is going to be 2r secant theta. So let's call this point as point A. So if the angular velocity of the rigid body is omega, then the velocity of point A is going to be 2r secant theta multiplied by omega, right? Because the perpendicular distance from the axis of rotation is 2r secant theta. And similarly, velocity of point B is going to be 2r tan theta multiplied by omega. Once again, because the perpendicular distance is 2r tan theta, right? Okay, so now let's locate the center of mass because we're interested in finding the moment of inertia, right? So the center of mass is somewhere over here such that this distance is equal to r. So now obviously this small triangle is going to be a right triangle as well. So this is the hypotenuse and the length of this is going to be r times square root 1 plus 4 tan square theta. Okay, so this just becomes square root 17 times r. Now for a thin rod, we know that the moment of inertia about the center is actually ml squared by 12, right? So the moment of inertia about the instantaneous axis of rotation, we can use parallel axis theorem. So ICM is going to be ml squared by 12, right? And plus the md squared term would be m times root 17r squared. So that will be 17r squared. Now the length of the rod is equal to 2r. The 4 gets cancelled out and this will become ml square mr square by 3. So this term would become 52 by 3 mr squared. Okay, so we have now determined the I about the instantaneous axis of rotation. So the kinetic energy of the rigid body is just half I times omega squared. Okay, so now we can just use energy conservation. We can just say that the increase in kinetic energy, which is this particular value, is equal to the decrease in potential energy. Okay, and the decrease in height, if you remember, it was r by root 2 minus r sine theta by 2. Tan theta was equal to 2, so sine theta will be equal to 2 by root 5. So this would be mg times r by root 2 minus r by 2 times sine theta. And now if you just rearrange, you'll get this particular value as the angular velocity of the rod. Okay, so that actually matches with option B. Okay, so the answer to that question is going to be option B, and r is just given to be 1 meter. So that's the reason why it's not present over here. Now in the next two questions, they're asking the speed of the NB and the speed of the point A. So that we already figured out here, right? So to the angular velocity, we have to multiply 2 secant theta because r is just 1 meter, right? So secant theta is going to be root 5. So for the velocity of point A, it's going to be 2 root 5 multiplied by omega. Okay, so if you observe the A option over here is actually 2 root 5 multiplied by omega. So the answer to this question will be A. And for the velocity of point B, we have to multiply it with 2 tan theta, which is just 4. So that will be 4 omega. Okay, so it's not A and it's not B. So actually the option doesn't really match in this case. Now option C states that when the upper end B reaches the surface of the cylinder, the velocity of center of mass of the rod is not horizontal, which is actually true because we can easily see that. Because the velocity of the center of mass will be in this direction, which is perpendicular to the line connecting IAOR to the center of mass, right? So this is clearly not horizontal. So this velocity is clearly not horizontal. So option C is actually correct. Now in option D, they're saying the distance between the center of mass and the instantaneous axis of rotation is root 15r, which is also not true because it's root 17r, right? So yeah, that's the discussion for this question. Now let's move to the next one. Okay, so this is the next question. So we have 3 small discs that are connected with 2 identical massless rods as shown in the figure. The rods are pinned to the disc such that the angle between them can change freely. Okay, so basically the length of these rods cannot change, but it is allowed to rotate around the disc. So basically it's a rigid rod that can freely rotate around the disc center. Now the system is placed on a smooth horizontal surface with discs A and B touching a smooth wall and the angle ACB being 90 degrees. So this angle is actually forming a right angle. A force F is applied on the disc C in a direction perpendicular to the wall. The acceleration of disc B immediately after the force starts to act is. So we want to find the acceleration of the bottom disc, and the mass of A and C is m and the mass of the disc B is actually 2m. So now first let's talk about the things that are very straightforward. By intuition we can see that this disc over here, the center of mass of this disc will accelerate in the upward direction. So I'm just going to call it as, okay, firstly the motion is happening in the horizontal plane. Okay, so don't get confused that why I'm not including gravity. It's because gravity is into the page. Okay, so now the thing is, guys, this disc over here, it cannot pierce through the wall, right? Which means its acceleration must be parallel to the wall or in the upward direction. Okay, so this was disc A, this is B, and this is C. So I'm going to call the acceleration of disc A as A capital A. Okay, and similarly the acceleration of disc B as A capital B. So now the thing about the disc C is that we cannot say directly that its acceleration is going to be vertical or horizontal because that will depend on some more factors. So either we can just say that it has a y component and an x component and work with this, or we can use a slightly different trick. Okay, so firstly, if you observe, this angle theta will reduce as the disc C comes closer to the wall and this guy moves upwards, right? So that we can easily see. So which means the rod will have some clockwise angular acceleration. Let's call it as alpha 1. Now similarly, this angle over here will also decrease, right? Which means this guy's angular acceleration will be in the counterclockwise direction. Let's call it alpha 2 because they don't necessarily have to be equal. Okay, so now if you just observe this disc A over here, how is it moving in the upward direction? It's because the tension force from this rod is actually pushing the disc A in the upward direction. So we can say that the rods are actually compressed. Okay, that's why the tension is pushing in nature. So here also the tensile force will push the disc C. So let's say that the tension in the upper rod is actually T1. The tension in the lower rod is actually T2. Okay guys, so now the thing is this angle was actually given to us to be 90 degrees. So I'm going to slightly redraw the diagram. Okay, so now it looks more like a 90-degree angle. Okay, so now we have to talk about the acceleration of this disc C over here. Okay, so now I'm going to name the centers of these discs as C1, C2 and C3. Okay, so now the thing is we are going to observe the center C3 with respect to the center C1. Okay, so now obviously guys, if we observe with respect to the center C1, then C1 will be fixed. Now if C1 is fixed and we know that this rod's length cannot change, then the acceleration in this frame must be perpendicular to the rod. Okay, so now let's just try to draw the acceleration diagram. So we are observing the center C3 with respect to the center C1. So if I fix the center C1, we know that this rod over here, let's say its length is L, we know the length of the rod, we know the length of this rod cannot change, right? Which means this point C3 can only have a tangential acceleration. It cannot have a normal acceleration. And we know the alpha is clockwise, so its acceleration will be alpha 1 multiplied by L. Okay, so this alpha 1 multiplied by L is the acceleration of the center C3 with respect to the center C1. Okay, so now if we add the acceleration of C1 vectorially to this, so the acceleration of center C1 is actually AA. The vector addition of these two components should give me the acceleration of C3 in the ground frame. Okay, so basically all I have done is that acceleration of C3 is equal to acceleration of C3 with respect to C1 plus acceleration of C1, right? So to the relative acceleration, if I add the acceleration of the frame, then I get the acceleration of C3 with respect to ground frame. So this is a geometrical fact. So if you observe this alpha 1 multiplied by L is along the rod C2, C3, right? Because this angle is actually a 90 degree, okay? And we know alpha 1 L is perpendicular to the rod. So alpha 1 L turns out to be in the direction of C2, C3. Now the thing is, we can use the exact same logic to the center C2, right? We can observe the center C3 with respect to the center C2. So for this, I'm using the yellow color. If we do that, we'll observe a relative acceleration of alpha 2 multiplied by L, which will be along the rod C1, C3, right? And then we have to add the acceleration of B vectorially. Even this should give me the acceleration of center C3. Right? Because all we are doing is writing the acceleration of C3 in two different ways. So the resultant of these two yellow vectors should be the same as the resultant of these two blue vectors. So let's write the acceleration of C in the y direction. Okay, so let's call it as ACY. So considering just the blue vectors first, it will be AA minus alpha 1 L by root 2. Why is the root 2? Because this angle is 45 degree. And that we can easily see by observing this triangle. So these two lengths are L and this angle is 90 degree. So the angle theta is actually 45. So you can basically do some trigonometry and figure out that all these angles are just 45 degrees, right? So this is ACY in the vertically upward direction, and towards the left, ACX is actually equal to alpha 1 L by root 2, right? So break down this alpha 1 L in the horizontal direction, it will be by root 2. Okay, this is writing the acceleration using the blue vector definition, right? Now let's do the same with the yellow vector definition. So this exact thing should also be equal to alpha 2L by root 2, because we are writing the acceleration in the upward direction. Okay, and AB is opposite, so this will be minus AB. And ACX is quite is simple. It will be alpha 2L cos 45, right? So this is going to be alpha 2L divided by root 2. Now the ACX expression is giving us that the magnitude of both the alphas are actually equal. Okay, so we can just consider this as some common alpha. And now if we substitute alpha 1 and alpha 2 as alpha in the first equation, what we get is acceleration of A plus acceleration of B equals square root of 2 L alpha. Okay, so this is an equation that we're getting. So now let's look at the forces. So in the first rod, I said that the compressive force on the rods are T1 and T2. So the component of tension that is accelerating the disc A is T1 by root 2, right? And it's providing an acceleration of AA. So I can write T1 by root 2 as M times AA, right? Now similarly, I can write T2 by root 2, 2m, because the mass of B is 2m, times acceleration of B. Okay, so let's just write that down here. Now let's talk about the disc C. So in the disc C, in the horizontal direction, we have a force, and then we have tension trying to push it away by both the rods. And there will be a cos 45 component acting in the horizontal direction. Okay, so on the disc C, we have F towards the left and T1 plus T2 divided by root 2 towards the right, and the acceleration in the x direction is alpha L by root 2, right? Okay, so now let's write down the F equals to ma equation. So F minus T1 plus T2 by root 2 will be m alpha L by root 2. Okay, so basically now we have 4 equations and we have 5 variables, right? So T1, T2, alpha, AB, AA. So we have 5 variables. We need one more relation. So for that, we can either use like Fy equals ma for may for the disc C, or what we can do is we can see that there is no force in the vertical direction, right? So basically I'm talking about the direction parallel to the wall. There is no force in this direction if we take all the 3 discs as our system. So if I'm saying that this direction is the y direction, then I can say the acceleration of the center of mass of the system in the y direction is actually 0. So we can say that m times AA, so this is in the acceleration of A is in the y direction, plus m times acceleration of disc C in the y direction. If you observe, it is AA minus L alpha by root 2. So this will be AA minus L alpha by root 2, plus the acceleration of the 2m mass is actually minus AB in the downward direction. So this should be equal to 0. Right? Okay, so now here instead of L alpha, I'm gonna substitute this particular value, and this becomes AB plus AA divided by 2. Okay, so from here we get acceleration of B as 3/5 of acceleration of A. Okay, so now basically we can substitute everything into this equation and we can solve for acceleration of B. So, and once you substitute everything in terms of AB, then you get the answer for AB as F by 5m. Now this is what they asked in the question. So you can basically solve for acceleration of A as well. So now if you want to determine T1, T2, alpha, all you have to do is substitute everything back. Okay, so that's it for this question, guys. So now let's move on to one more question. Okay, so this is question 1.248 from Irodov. So this was requested by a few of you guys. So and the question is, we have a uniform cylinder whose radius is r that is spinned about an axis to the angular velocity of omega naught. Okay, so this cylinder over here, it initially had an angular velocity of omega naught, and then it is placed into a corner. The coefficient of friction between the corner walls and the cylinder is equal to k. How many turns will the cylinder accomplish before it stops? Okay, so obviously it'll start to decelerate, and after some time it'll come to rest. Okay, so the disk had a counterclockwise angular velocity of omega naught. Okay guys, so firstly here we'll work with the assumption that the center of mass remains in its place. Okay, so basically the cylinder is not moving horizontally is what I'm saying. So in this case what happens is the point of a cylinder in contact with the left vertical wall is slipping in the downward direction, right? Because the omega is in the counterclockwise sense, so this point will slip in the downward direction. So the kinetic friction force on the cylinder will be in the vertically upward direction, so I'm going to call it as F1, and the normal reaction applied by the surface as N1. Okay, and let's say the normal reaction from the bottom surface is actually, and the bottom point is slipping in the rightward direction, so kinetic friction will be in the leftward direction. And then finally we have to mark the weight of the cylinder. Okay, so this is the complete FBD of the cylinder. Now obviously, if the center of mass is remaining in this place, we can say sigma fx and sigma fy equals 0. So this directly implies N1 equals F2 and N2 plus F1 equals mg. Okay, and now we also know that the friction forces are kinetic in nature. So F2 I can write it as K, which is the friction coefficient, times N2, right? Similarly, F1 I can write it as K times N1. Okay, so now we can solve for N1 and N2 from these two equations, and we'll get these particular values. And now once we have the normal reaction, we have determined the magnitude of F1 and F2 as well. So okay, so now once again the angular velocity was in the counterclockwise sense, but if you observe, the friction forces are providing a clockwise angular acceleration trying to decelerate it, right? So we can apply tau equal to I alpha about the center of mass. So the torque of F1 plus F2 would be the moment of inertia about the center of mass of the cylinder times the angular acceleration alpha. So F1 and F2 are mu n1 and mu n2. So once you substitute F1 and F2, we'll get this value for the angular acceleration. In fact, it'll be the angular deceleration. Okay, so now the thing is, it's obviously a constant angular deceleration, which means we can use the formula for uniform acceleration. So that was omega square equals omega naught square plus 2 alpha theta, right? So the final omega is going to be 0 because we're talking about the instant when it comes to rest, and the initial omega is given to be omega naught minus 2. Okay, so let's substitute the value of alpha. And for the angle covered, in the question they wanted us to find the number of turns. Okay, so the angle covered, I'm going to write it as the number of turns n times 2 pi. Okay, so each turn corresponds to 2 pi angle. So n turn corresponds to 2n pi angle, right? So now we can solve for n from this equation. Okay, and once you solve this, you'll get the number of turns as this particular expression. So yeah, that was it for this question. Okay, so that was it for this video, guys. If you have any doubts, you can comment down below, and if you enjoyed the video, do like, share and subscribe, and that's it. Thanks for watching.